Hello students, I am Vishwanath. Welcome to my YouTube channel. Today I am going to discuss about the refraction of light through plane surface. In this topic I shall discuss about the Snell's law, general form of Snell's law, the apparent depth of an object placed in water, the field of view of fish in water, and the working principle of optical fiber, etc. I think you all enjoy my video, and please click the like button if you like this video, and please subscribe my channel. Let's watch the video. Hello student, today's topic of discussion is refraction of light through plane surface. There are two media, first and second. The first medium is rarer medium, say air, and the second medium is denser, say water. AB is an incident ray, comes from rarer medium and moves through the denser medium. After refraction, the refracted ray moves towards the normal drawn at the point of incident on the plane normal on the plane of the divided division, plane of division between two medium, that is x prime x here, the medium which separates the two media. Here AB is the incident ray, BC is the refracted ray, I1 is the angle of incidence and I2 is the angle of refraction. On the other hand, when a light ray comes from denser medium and moves through rarer medium, then the refracted ray moves away from the normal drawn at the point of incident on the plane of separation, that is on the x prime x. Here CB is the incident ray, BA is the refracted ray, I2 is the incident angle and I1 is the refracted angle. This phenomena is known as refraction of light. In the refraction of light, there are two laws. First law states that the incident ray, the refracted ray, and the normal drawn at the point of incident on the plane of separation lie at the same plane. That is, that AB, BC, and N1, N2 lie at same plane. Here on the plane of the board. And the second law states that the sine of angle of incident to the sine of angle of refraction is equal to constant. That is, ratio between the sine of angle of incident to the angle of refraction always remain constant. This constant is known as refractive index of the second medium with respect to first medium. Let AB is the incident ray, BC is the refracted ray according to first figure, and N1, N2 is normal to x prime x, where x prime x is the plane of separation between the two medium, rarer medium and denser medium. I1 is the angle of incident, I2 is the angle of refraction. Therefore, sin I1 by sin I2 is equal to 1 mu is equal to constant, where 1 mu 2 is known as refractive index of second medium with respect to first medium. The value of 1 mu 2 depends on the nature of two medium mediums and the wavelength of the light used. If mu1 and is the absolute refractive index of first medium and mu2 is the absolute refractive index of the second medium, and Ri stands for refractive index, then 1 mu2 is equal to mu2 by mu1, that is refractive index of second medium with respect to first medium is equal to refractive index of second medium by refractive index of first medium. Now let v1 and v2 be the velocities of light in first and second medium respectively. Then mu1 is equal to c by v1 and mu2 is equal to c by v2. Okay, where c is the velocity of light in the vacuum. From these two relations we can write that 1 mu2, that is refractive index of second medium with respect to first medium, this is equal to refractive velocity of light in first medium by velocity of light in second medium. That is, refractive index of a medium is inversely proportional to the velocities of light in that medium. Now the relation between wavelength of light lambda and refractive index mu of a medium. This is given by mu is equal to a plus b by lambda square from Cauchy's theorem. But for simplicity we can write mu is equal to d by lambda, where a, b, d all are constants. That is, when light passes through one medium to another medium, its frequency does not change, but velocity may change. This is the reason of refraction of light. That is, when light passes through one medium to another optical denser medium, then the frequency does not change, but velocity changes. Optically denser medium, then its frequency does not changes, but velocity changes. This is the reason of refraction of light. Now we are going to discuss about the general form of Snell's law. There are three media having refractive index mu1, mu2 and mu3 respectively. Here first media have refractive index refractive index mu1, second medium have refractive index mu2, third medium have refractive index mu3, and again the first medium have refractive index mu1. AB is incident ray in the first medium, BC is refracted ray in the second medium, CD is refracted ray in the third medium, again DE is the refracted ray in the first medium. X1, X2, X3, X4, X5, X6 are the plane separated these mediums and they are parallel to each other. N1, N2 is N1, N2, N3, N4, N5, N6 are normal drawn at the point of incident. Here I1 is the angle of incident in the first medium, I2 is the angle of refraction in the second medium. It is also the angle of incident in the second medium. I3 is the angle of refraction in the third medium. Also I3 is the angle of incident in the third medium. I4 is the emergent ray, that is refracted angle of refraction in the last medium. Since N1, N2 since N1, N2 parallel to N3, N4. That's why angle N2BC is equal to angle BCN3. N2BC is equal to angle BCN3. This is equal to angle I2. Okay. Similarly, we can write that angle N4CD is equal to angle CDN5 is equal to angle I3. Okay. Now we can write that sin I by sin R is equal to sin I1 by sin I2 is equal to mu 1 to 2 is equal to mu 2 by mu 1. Sin I2 by sin I3 is equal to mu 2 to 3 is equal to mu 3 by mu 2. Okay. Similarly, sin I3 by sin I4 is equal to mu 3 to 4 is equal to mu 4 mu 1 by mu 3, because mu 4 and mu 1 are same. Okay. Now multiplying this, we can get sin I1 by sin I2 into sin I2 by sin I3 into sin I3 by sin I4 is equal to 1. Therefore, sin I1 is equal to sin I4. This gives I1 is equal to I4. Therefore, AB is parallel to DE. That is, incident ray and emergent ray are parallel to each other when the first medium and the last medium are same. When the first medium and last medium are same, then the incident ray and emergent ray are parallel to each other. From the above relation, we can write mu1 sin I1 is equal to mu2 sin I2 is equal to mu3 sin I3 and so on. This is known as general form of Snell's law. This is known as general form of Snell's law. Now we are going to discuss about the refraction of light through a rectangular glass slab. Let A, B, C, D is a rectangular glass slab having refractive index mu with respect to light. PQ is incident light ray on the surface AD. QR is the refracted light ray and inside the glass slab, and RS is also the emergent ray or refracted light ray from glass to air. From Snell's general law of radiation, we already know that PQ is parallel to RS. You can prove it from general Snell's law. Okay. Now we draw a normal from the point R to the extended PQ. They intersect at the point E. That's why RE is the lateral shift of the light ray. Let T is the width or thickness of the glass slab. Now RE, lateral shift of the light ray, RE is equal to sine angle RQE. Okay, this is 90 degree. RE is equal to sine RQE, and you know that angle RQE is the angular displacement, angular deviation of light ray due to refraction. This is equal to sine I1 minus I2, where I1 is the incident angle and I2 is the angle of refraction. Where and RE is equal to QR into sine angle RQA. QR into sine I1 minus I2. Now, from the triangle QN to R, we also write that QN2 is equal to QN2 is equal to cos QR into cos I2. Okay, because cos I2 is equal to QN2 by QR. This gives QR is equal to QN2 by cos I2. QN2 by cos I2. QN2 is equal to thickness T of the glass slab by cos I2. Therefore, lateral displacement is equal to T into sine I1 minus I2 by cos I2. Okay. From Snell's law, we can also write mu is equal to sine I1 by sine I2. From this relation, equation number 1 and equation number 2, you can also find the lateral displacement of the light. The next topic is critical angle and total internal reflection. Critical angle and total internal reflection. Let the first medium is a rarer medium, say air, and the second medium is denser medium, say water, and two medium is separated by a plane x prime x. N1 N2 is normal, drawn at the point of normal at the point of incident to the plane of separation, that is x prime x. Here AB is incident ray and BC is refracted ray. In this case, the light ray moves from denser to rarer medium. Denser to rarer medium. In this case, I2 is the angle of incident and I1 is the angle of refraction. You know that when light ray moves from denser to rarer, then the refracted ray moves away from the normal. That is, in this case, the angle of refraction is greater than angle of incident. When the angle of refraction is 90 degree, that is I1 is equal to 90 degree, then the angle of incident in the denser medium is known as critical angle of the second medium with respect to first medium. When I1 is equal to 90 degree, then I2 is equal to theta c, where theta c is known as critical angle of second medium with respect to first medium. Okay. In this case, AB is the incident ray and BC is the refracted ray. Okay. I1, I2 is equal to angle of incidence, and I1 is equal to angle of refraction. Okay. Now we are going to establish the relation between critical angle and refractive index of two medium. Let mu12 is the refractive index of second medium or denser medium with respect to first medium or rarer medium. Okay. Therefore, we can say that sine I1 by sine I2 is equal to mu1 to 2. This gives sine 90 degree by sine theta c is equal to mu1 to 2. Therefore, we can write that sine theta c is equal to mu to 1. Sine theta c is equal to mu to 1, or sine theta c is equal to mu1 by mu2. This is the relation between refractive index and the critical angle. When the light ray dB incident on the x prime x plane and the angle of incidence is greater than the critical angle. Here the angle of incidence dB into is greater than the critical angle theta c. Then the light ray reflected by the plane x prime x and bounce back to the denser medium, and it cannot reach from denser to rarer medium. That is, when the light ray moves from denser to rarer medium or tries to move from denser to rarer medium, and the angle of incidence is greater than the critical angle between the two medium, then the light ray is reflected by the plane of separation between the two mediums and again comes to the denser medium after reflection. This phenomena is known as total internal reflection. This phenomena is known as total internal reflection. That is, for internal reflection there are two conditions. First, the light ray should be moved from denser to rarer medium, and the angle of incidence on the plane of separation between the two medium is greater than the critical angle of the two mediums. Then the incident ray reflected by the plane of separation and comes back to the denser medium again. This phenomena is known as total internal reflection. Now the characteristics of total internal reflection. First, the light ray tries to move from denser to rarer medium. Second, the angle of incidence is greater than the critical angle of two media. And third, no light ray is absorbed or transmitted. Only total internal reflection occurred. These are the characteristics of total internal reflection. First, the light ray tries to move from denser to rarer medium. Second, the angle of incidence is greater than the critical angle of two media. And third, no light ray is absorbed or transmitted. Now, I am going to find out the relation between real depth and apparent depth of an object placed inside a denser medium and observer is in the rarer medium. Okay, you know that when we placed a coin inside a empty bucket, then the depth is greater than when the bucket is filled with water. That is, when the bucket is filled with some water, then the coin is appeared to moves at high. Let P is the position of the coin, or P is the point object, and P prime is the image of P. That is, here apparent depth is PQ and real depth is PQ. Here real depth is PQ and apparent depth is P prime Q. Here apparent depth is less than the real depth PQ. Now we have to find out the relation between PQ and P prime Q. Okay. Here PO is the incident light ray and O is the refracted light ray. When we extended EO, then it intersects PQ at the point P prime. Here PQ is normal to the plane of separation between the denser and rarer medium x prime x. Say the rarer medium is air having refractive index mu1 and it is water refractive index mu2. That is, the refractive index of water with respect to air is 1 mu2. Okay, this is first medium and water is considered as second medium. The angle of incident in the second medium is I2 and angle of diffraction in the first medium is I1. This is first medium and this is second medium. Water is second medium. Okay. Since N1, N2 is parallel to OR, that's why angle QPO is equal to angle PON2 is equal to I2 and angle N1OE is equal to angle QPO. Then we can write, since PQ is parallel to N1, N2, therefore angle QPO is equal to PON2 is equal to I2 and QP prime O is equal to N1 OE is equal to I1. PQ is the real depth and P prime Q is the apparent depth. We know 1 mu 2, that is refractive index of second medium with respect to first medium, that is refractive index of denser medium with respect to rarer medium, is equal to sin I1 by sin I2. This is approximately equal to tan I1 by tan I2. Since the values of I1 and I2 are very small, that's why we can write sin I1 approximately is equal to tan I1 and sin I2 approximately is equal to tan I2. From this figure we can write tan I1 is equal to OQ by P prime Q and tan I2 is equal to OQ by PQ. This gives 1 mu 2 is equal to PQ by P prime Q. Okay, this is equal to real depth by apparent depth. This is the relation between real depth and apparent depth with the refractive index of the denser medium with respect to the rarer medium. Okay. Now we are going to find out the relation between real height and apparent height of an object when the object is placed in the rarer medium and the observer is in denser medium. That is, when the object P is placed in air and the observer at E is in water, and 1 mu 2 is the refractive index of water with respect to the air. Okay, here in this case the rarer medium is known as first medium and the denser medium is considered as second medium. In this case, PO is incident ray and OE is the refracted ray. When we extended EO, it intersects the line RQP at the point P prime. That's why P prime is the image of P, where PQR is normal to X prime X. X prime is the plane which separates the two medium, rarer medium and denser medium. In this case, I1 is the angle of incident and I2 is the angle of refraction. Since P prime R is parallel to N1, N2, that's why QPO is equal to N1OP is equal to I1 and P prime O is equal to N1 O P prime is equal to I2. Okay. This is equal to I2. And we know N2OE is the angle of refraction and P prime O N1 is vertically opposite to N2OE. That's why P prime O is equal to P prime O N1. Since P prime Q is parallel to N1 N2, therefore angle QPO is equal to angle PO N1 is equal to I1. That is, angle QPO is equal to angle PO N1 is equal to I1 is equal to angle of incident, and angle P prime O is equal to angle PO N1 P prime O is equal to angle P prime O N1 P prime O N1 is equal to N2OE is equal to N2OE, because P prime O N1 is vertically opposite to N2OE, is equal to I2, is equal to angle of refraction. Now you know that 1 mu 2, that is refractive index of second medium with respect to first medium, is equal to sin I1 by sin I2, approximately equal to tan I1 by tan I2, because I1 and I2 are very small angles. Therefore, 1 mu 2, that is refractive index of denser medium with respect to rarer medium, is equal to tan I1 is equal to OQ by PQ, and tan I2 is equal to OQ by P prime Q. This gives P prime Q by PQ, that is refractive index of second medium with respect to first medium is equal to P prime Q, is equal to apparent height by real height of the object. This is the relation between the refractive index of the medium, denser medium with respect to rarer medium with the real height and apparent height of the object. Now I am going to discuss about the field of view of eye under water. Let a fish is inside a water, C is its eye, and x prime x is the plane of separation between air and water, which is horizontal. CB is the incident light ray and BX is the refracted light ray. Similarly, CA is the incident light ray and AX prime is the refracted light ray. Here theta C is the critical angle between water and air. Theta C is the critical angle between water and air. O is the midpoint of AB. In this case, ACO forms a cone. O is the center of the base of this cone, or O is the center of the circular base of the cone. AB is the diameter of the base of the cone. The fish can see the outside view through this cone, and the same vertical angle is 2 theta c, and semi-vertical angle is theta c. Here OC is equal to depth of the fish H. OB is equal to small r, is equal to radius of the cone or radius of the base of the cone. OB is equal to small r. Now tan theta c is equal to r by h, perpendicular by base, and we know tan theta c is equal to sin by cos theta c is equal to r by h. This gives r is equal to h into sin theta c by cos theta c. This is equal to sin theta c by root over of 1 minus sin square theta c. we know sin theta c is equal to 1 by mu, where mu is the refractive index of water with respect to air. Theta c is equal to mu 1 by mu air to water. Therefore, we can write h into root over of mu h by mu root over of mu square minus 1. This is the relation between the radius of the base of the cone and the height of the cone. Now I am going to discuss about the working principle of an optical fiber. This is a figure of optical fiber. Here an optical fiber has mainly three parts. Inside medium is known as core, and next medium is known as cladding, and last medium is the coating of the fiber, optical fiber. The last or outsider medium is an opaque and it is hard medium, but inside the two media are transparent. Refractive index of core is greater than the refractive index of cladding, and refractive index of cladding is greater than the refractive index of air or outside medium. Here the radius of the optical fiber or the radius of the core is very small. It is less than 10 to the power minus 6 meter. That is, inside radius of the optical fiber is very small. It is less than 10 to the power minus 6 meter. When a light ray enters into the optical fiber, then it tries to move from denser to rarer medium. But due to the total internal reflection, it reaches from one end to the other end of the optical fiber. Since in this case total internal reflection occurs for the light ray, therefore no signal is lost and no heat loss is occurred. That's why it is better than copper wire or any kind of metal wire for signal transmission. Okay. Now I am going to discuss about the numerical aperture of an optical fiber. Let x prime x is the axis of an optical fiber. AB is the incident light ray, which makes an angle theta with the axis of the optical fiber. The numerical aperture of the optical fiber NA is equal to sin theta is equal to under root of mu 3 square minus mu 2 square by mu 1 square. You know that mu 3 is the absolute refractive index of core, and mu 2 is the absolute refractive index of cladding, and mu 1 is the absolute refractive index of the surrounding. Here theta denotes the maximum value of the angle of incident for which we can get the light ray on the other side of the optical fiber. This is known as numerical aperture. Here theta is the maximum value of incident angle of light ray for which we can get emergent light at the other side of the optical fiber. This is the end of our discussion for today. I think you understand this topic, you have any queries related to this chapter, then please write it in the comment box and I shall solve those. Okay, if you like my video, then please click the like button and please subscribe my channel. Your subscription encourage me to make another video. Please subscribe my channel. Thank you for watching my video. Okay, goodbye, take care.